All right, young scientists, let's pick up back here with acids and bases, and we're actually going to put the pieces together with some things you've already learned about equilibrium. Because acids and bases will dissociate, they'll break apart in solution to an equilibrium, and you already know how to do those calculations. You already know how to find a K expression, and now all we're doing is tagging an A or a B onto that. K for an acid, we call Ka. K for a base, we call Kb. Our dissociation reaction for an acid will look something like this, where A is just whatever your acid is, whether it's chlorine or iodine or the acetate ion, doesn't matter. But your HA breaks apart into H3O plus. It could be written this way. You also could just write it as H plus and A minus. Or your base becomes BH plus and OH minus. And then, just like for any other equilibrium, we don't care about solids, liquids, and gases. They don't have concentrations. So your Ka expression is your H3O plus, or you might call this H plus, times A minus over HA. Or your Kb expression is OH minus times BH plus over B. It's the same thing we've done before. Now, one extra piece of information that can be useful. Ka times Kb for any acid and its conjugate or any base and its conjugate is the same as Kw, or the K for water. And before we said that that was 1 times 10 to the minus 14th. This is the same 1 times 10 to the minus 14th that you get from H plus times OH minus. These things all go together. If you actually plugged all of the equations in, you would see that everything would fall out except for H plus and OH minus, because that's our net ionic. So this might look scary, but actually these are all things you already know how to do. Go ahead and pause the video and write the Ka expression for H2SO4 breaking apart into H pluses and SO4 minus 2. And label, since it's reacting with water, the acid, the base, the conjugate acid, and the conjugate base. Go ahead and pause the video and do those things. Okay, here's another very similar problem for you. And this time it's going to be Kb instead of Ka for NH3 reacting with water to make NH4 plus and OH minus. Go ahead and label the acid, base, conjugate acid, and conjugate base, and write the Kb expression. Pause the video and do those things. Now, one of our methods for finding the strength of an acid or a base is called titration. It's where you add an acid or a base to the opposite one until they reach an equivalence point. And old school, we used to find out how we got to that equivalence point by adding an indicator. Some of you may remember from Chem 2 doing this lab with phenolphthalein. And you're really, really trying to get a very, very faint color change with that indicator. I think most of you saw that it turned bright pink when you did it. That means that you went too far. This is a very accurate method, but it takes a lot of skill. So in the 21st century, we usually use a pH probe instead. And that'll help us find the concentration of an unknown. Now, if you graph this over time, you get what's called a titration curve. And this is one of the things that the pH probe would spit out on the computer for you, where it starts out being very acidic, very acidic, very acidic, and then once you've added enough base to get close to neutralizing it, suddenly the pH changes very drastically with not adding very much base. This is also why it's really easy to overshoot and end up with a really pink solution, because adding just a little bit more base jumps the pH up really high. Now, if you've taken calculus, you'll know about inflection points. If you haven't, that's okay. There's a point here where the rate of change flips, and that's called the equivalence point, and that's our end point. That's when we've actually added equal amounts of each acid to base. Don't stress about that too much. Now, if we add a strong acid to a strong base, we're assuming that they 100% dissociate. This is actually pretty easy. You just react your H pluses with your OH minuses, and whatever you have left over, whatever's not your limiting reactant, you use that to find the pH. So if I figure out that I have 10 moles of H plus and 5 moles of OH minus, well, those 5 moles will react, and I'll have 5 moles of H plus left over, and I do my pH math from there. Strong reactions are not that challenging. First, let's do a little bit of review. Make sure that you can calculate the pH of 0.50 molar calcium hydroxide. Now look at this. Remember, there are 2 OHs in calcium hydroxide. So factor that in when you're trying to find the OH concentration. Then work your way to pH. Pause the video and try that. Now we're starting to really build up. Write the dissociation reaction for HNO3. This is nitric acid with water. Label the acid, the base, the conjugate acid, and the conjugate base. Hopefully you're getting enough repetitions in on this that this is getting easier. Go ahead and pause the video and try that. Okay, now this looks scary. Don't panic. Ka for acetic acid, for vinegar, is 1.8 times 10 to the minus 5th. Ka for HClO, hypochlorous acid, is 3 times 10 to the minus 8th. Which one is stronger? We're not going to do any math. Which of these numbers is bigger? 10 to the minus 5th is bigger than 10 to the minus 8th. That means that this one is more product favored. It's stronger. Acetic acid is stronger. Now with that knowledge, remember, stronger acids make weaker conjugates. Which base, based off of those, is stronger? Well, if acetic acid is stronger, that means its conjugate base, acetate, is weaker. And the ClO minus will be a stronger conjugate base. I want you to calculate the KBs for both. Again, this isn't hard. Don't panic. Remember, Ka times Kb is always 10 to the minus 14th. So 1.8 times 10 to the minus 5th times the Kb that you want to find equals 10 to the minus 14th. Go ahead and find that for both of these. Now, when we have a weak acid or a weak base, they don't completely dissociate. You're going to basically just treat these as equilibrium problems, because they really are. You know how to do this, you just haven't done it with acids and bases yet. There's a whole big set of steps here, but I'm not going to walk through it, because actually you've seen this set of steps before. We're going to use some ice tables. We're going to solve. If we have a small k value, then we don't care about subtracting x. These are all things you've done before. So if we look at this problem, we want to know the pH of 1 molar HF, hydrofluoric acid. HF has a Ka of 7.2 times 10 to the minus 4th. Water has a Ka of 1 times 10 to the minus 14th. Which one of these acids is stronger? Yeah, hopefully you can tell that 10 to the minus 4th is much, much bigger than 10 to the minus 14th. It's what? 10 billion times stronger. So we don't really care about the water. We just care about the HF. So our Ka expression is going to be H plus times F minus over HF. It's just a K expression. You've done that before. Now that we have our K expression, we need to find some equilibrium concentrations, which means we need an ice table. We said we were starting with 1 molar HF. We're going to lose X of that and gain X of H plus and F minus. So at equilibrium, we'll have 1 minus X of HF, X of H, and X of F. So our equilibrium expression is 7.2 times 10 to the minus 4th, the Ka, equals X times X, or X squared, over 1 minus X. Now you could go through and solve that with the quadratic formula and all that stuff, or you could say, this is a pretty small Ka. let's just ignore this minus x. 1 minus x is probably basically still 1. And then we say, okay, x squared over 1, or x squared, equals Ka. Take the square root, and x is 0.027 molar. That's our concentration of H+. Then you go back and say, okay, 1 minus 0.027 is 0.973. Those are basically the same number. Yeah, it's fine that we did this. It's within 5%. So we've got H+. To find the pH, we just take the negative log of that number. 2.7 times 10 to the minus second is 0.027. The negative log is 1.57, so our pH is 1.57. Everything up to this point, and really even checking our math here, was all just an equilibrium problem. And then you took the negative log of your answer to find the pH. Nothing that should be too new or scary here. Now we could also talk about the percent dissociation for weak acids. And the percent dissociation is just a percentage. How much of it broke apart divided by how much there was at the start times 100. So on our last one, 0.027 broke apart. There was 1 to start, so our percent dissociation is 2.7%. It's just taking a percentage. So here, can you please calculate the percentage dissociation for acetic acid with this Ka and this initial concentration? It's the same as the last problem, just with a new Ka. Go ahead and pause the video and give that a shot. Okay, here's a little bit different problem. I want you to calculate the molar concentration of OH. I want the concentration of OH minus. Here's your starting concentration of this compound and the Kb. I also want you to calculate the pH. Now to help you out just a little bit here, this C2H5NH2, it's going to add a hydrogen from the water and become C2H5NH3+. You can tell that because Kb is bigger than 10 to the minus 7th. This means it's better at being a base than an acid. So write out your reaction. C2H5NH2 plus H2O makes C2H5NH3 plus OH minus. Use Kb to work through and find the OH concentration. Then work your way around the circle to find the pH. This is a more involved problem. It's probably going to take you a minute. Go ahead and pause the video and work on it. We can talk about it in class. This is also where I'm going to cut off for this video. I don't want to go into the next topic. These are all equilibrium problems. If you just think about them that way, they aren't as scary looking. Yes, there's a few new vocab terms. Yes, we add 1 or 2 more equations that are pretty straightforward on the end. Don't panic about this stuff, kids.